Hello developers, let's start developing. Today we're taking on the 20th task of the 2024 Advent of Code. And it's an interesting one that's kind of connected to the previous mazes that we had to do. So this time we have a racetrack, basically the race condition festival. If you've never had a race condition in your code, great. You don't want those, they're incredibly hard to debug. Fortunately, this is just called a race condition, and we're racing. So we have a single racetrack that kind of winds through everything. So let's start by parsing the input. So what is our input? So basically it's gonna be relatively simple. We're just gonna lines dot map, and each line we're gonna split on line dot split. Come on literally everything, and we get the maze, which means that instead of a string array, we're gonna have a string matrix. Yeah, we can make it a bit better, but so we can make a type that will only allow that to be a hash, which is a wall, a dot, which is a part of the racetrack, an S, which is the start position, or an E, but we can do that later. Let's just do print matrix of the input so that we know that we did it okay. We're supposed to get this picture. And that's kind of what we get. So now I'm gonna solve basically the zeroth part, which is gonna find a path through the grid. Then there's supposed to be only a single path, so I will actually test for that. So how do we do that? Well, it's gonna be simple. We're gonna have our maze as a something else. So now I will say we have a type that's maze. It's not gonna be string. It's gonna be something like this. We're gonna have our start, which is gonna be a point. Yeah, sometimes I will use this as coordinates, but to be honest, I prefer this as well. We have start, which is a point, the end, which is a point, and note that if we eliminate and extract the start and the end from the grid, then we're left with only two types, ones we can go through and ones we cannot go through. So it's a wall or a not a wall. So I will actually, the maze will be a matrix of things where each thing has a value which will be not a string. Now we can go much more detailed. It's gonna be either a dot or a hash. We can use booleans here, but this reason is easier for printing. And each maze will also have a price or distance, which is the distance from the start, which means the start has a distance of 0, the one next to it has a distance of 1, and so on and so forth. So I will actually do this now. So let's have that const make maze. We take an input that is a string, and we're gonna return the maze. No, we're not gonna do that. So we're gonna do a for loop. We're gonna for loop through the mazes rows rows. This is our index. This is our input. We're gonna have our, we don't even need this, we don't need the row, we can, yes. So something along these lines, only the difference is when we're not doing AA and ZZ, we're using S and E. So we're gonna set the start and the end. We can optimize this so we don't go through literally everything after we find the start and the end. Let's have those in constant, and now I will initialize the maze, something like this. And the value distance is gonna be number dot max safe integer initially. So what this does, takes each row, maps each cell in each row to something like this. The object that we want to have a value, which the cell will be. But this is gonna be wrong, because right now our value can also be S and E. So what we will do, we're gonna remove those. So input, but using this we're gonna destroy the input. And we don't wanna do that, which means that we're gonna have a copy. And in that case, let's use the copy everywhere. Actually, when I need to do something like this, I would rather call this input and call this source. So right now I know that I won't be changing the source since nobody used source until now. So we're gonna have S and E are now simple dots. We have our distance, and now we're gonna, yeah, let's start it with this. Let's see if we can, oh, prepend listener. This is not something that I wanted to do. I wanted to use the print matrix. Yeah, and we're gonna basically map the values. So we should get the exact same image, only without S and E, and we're gonna have dots over there. And since we're here, let's console log the start and the end as well. The maze looks okay, whether the start and end look okay. 1, 3, 5, 7, somewhere around here, looks okay. So we got our maze initially. But now I will actually try to loop from the start to all the places. And you know what? Let's design this a bit better. We're gonna have a wall cell that is basically has a value which is a hash, and a type open cell which has a value of dot and has a distance which is a number. So now instead of having this will be a matrix of cells, and the type cell will be either a wall cell or an open cell. So this will be a literal cell array. Now our mapping will be totally wrong, because we cannot do this anymore. We're gonna need to do something a bit more complicated, but why not? A bit more complicated. The distance will be the maximal possible distance, since we didn't manage it so far. And by the way, when we have the maze.maze of start, and everything is gonna have a distance of 0. And now this won't allow me to set distance. Why? Because this is a cell. And this thing doesn't know whether the start cell is actually an open cell or not. So I will have to, I know that. So I will tell it, yeah, it is an open cell. And do that. I will also add a guard check here. Oh, we don't need that. We can have a much better cell. We can just cell dot value is that. We can also have this thing. So now we can say is open cell of that. It's gonna be longer. So this works since we are quite sure that this is thing. Okay. So while the queue is not empty, we're gonna get a cell. And the queue will have points. Yeah. No, this is the point. This is not the cell. The cell is this thing. And yeah, we know that we're gonna have a point. We will not do this. We will say if this is a wall cell, what are we doing here? Something went really wrong. But now we can see that cell actually is an open cell because TypeScript knows if it's not a wall cell, it's going to be an open cell because those are the two options. And it's not a wall cell, which means it's an open cell. So we can say cell.distance. I'm gonna do it the other way. So this, when I'm here, the distance will already be here. So I will just need to get the neighbors. You should be able to do this by yourselves, and we're gonna filter the neighbors like this. Of course, one thing that you see me always doing, we are gonna get the width. Actually, we're gonna do that way up high. So we can actually say here, this is the height and this is the width. So now we have this thing when we can filter out our neighbors. Let's imagine a better one. Yes. So it's between 0 and width and between 0 and height. And those are all the valid neighbors. And we're gonna also filter out the walls. Is open cell the equivalent maze for the neighbor? What do you mean cannot find the maze? You cannot find it because I added a semicolon here. So this should give us all the neighbors that are on a given point. And we're going to filter it once more. Yes, it's going to be something like this. I think that this is going to be needed. Yeah, because it knows it here. Oh, we're going to add it. We're going to be a bit shameless. I almost never do this. Ah, let's be a little bit less shameless and write this properly, and it's gonna be even better. So if this is an open cell, then distance. Oh, this is not our cell, this is the neighbor's cell. So if our neighbor's cell is, then the neighbor cell should be bigger than the cell distance plus 1. So we're returning the neighbors only if they are open and also they have a distance that is bigger than the distance if we came from this cell. So basically find the next one. If it's, so in our case, it's gonna be either this value or it's gonna be number.maxsafe integer, which means that nobody processed that neighbor so far. So we're getting specifically the next neighbor. One additional thing that I will do. So these neighbors should be basically a set of only one item. If the definition, I understand the definition correctly, which means that we have a track. So if we are here at this point, we can only have come from this point, so this already has a lesser distance, and we can only go to this point. So our filter will generate these 4 neighbors, our wall filter will eliminate these 2, and the price filter will eliminate this one, so we're only left with the next step. Yeah, if that's an open cell, otherwise it's a wall cell, we're gonna return false. So I will say if neighbors.length is, yeah, it can be 0, it's gonna be 0 at the end, is bigger than 1, we're gonna throw that we have more than one neighbor, which means we're solving the wrong task. Otherwise, we can just say take the first neighbor since it's only 1. And we're gonna enqueue it. Yeah, that's the neighboring cell. We're setting the distance and we're pushing it to the queue. Basically, we know that it's an open cell, so we don't have to do anything else. And we're gonna end the while on that note. So by doing this, we should get our maze. And I'm gonna print it now. And I'm gonna use something exactly like this. Thank you, Copilot. Only, yeah, you missed a parenthesis, and it's gonna be a bit different since I wanna use it like this. And if it's up to 3 digits, no, it's gonna be up to 2 digits, I think. It's gonna all the way up to 20, 30, 72, 84. So yeah, let's have it that way. So I'm gonna pad it to 3 using a space, and I'm gonna pad it to from the end using an additional space. So we should get nicely separated, nicely drawn out maze. Let's see if this works. It doesn't because we made a boo-boo somewhere on line 114. Let's see where that is. Huh? We shouldn't. These should basically filter out all of that. But of course, we can have bugs. Oh, 4757. The endpoint doesn't have any neighbors. When we get to the end, we kind of then have to finish. So, yeah, if it has more than one neighbor, that's okay. If it has no neighbors, we're just gonna continue and finish. We got to the end and we said, well, we wanna do more, we wanna do more. Well, you cannot. You're already at the end. Let's see what we got. Oh, so we're going that way and that way. Racing, racing, racing. We got to the end. You know what? I will now do the same thing with the big input bits because I'm quite interested whether we'll get this error or not. If we don't get this error, which means that my assumption is correct, and then I can code using that assumption. And a lot of code will be much simpler. Yay, we got a not as nice picture because I think that we can have more than 3 digits over here. What are we doing and why is it in part 2? Did I make an error in the code? Yeah, I don't know why, but I wrote all of this in part 2. I still have no idea what part 2 is. Yeah, let's leave that. So let's add a few dashes here, and then we can have this to be 4 and this to be 6. It should be enough. And now instead of returning this, let's just return the total length, and the total length will be this, the value of the distance of the. Anyway, we might want to have it looking a bit better. Let's save this as out.txt so that we can avoid the wrapped lines. Let's see now, we have this file, and if we zoom out, we can see what is happening, and the end is somewhere around here, I think, so it will be something like 10,000. The actual value, maximal value, is 9456. If we find this is, yeah, that's where the end goes. So yes, everything is like that. Let's just see if this is fit on this side, which means we don't have any max values that we're displaying. So we have a few assumptions checked out. One of those assumptions is that our track, we don't have a fork in the track. So we don't have a position when we actually have to decide whether we want to go left and right or right. We always know where to go. The other assumption is that we're gonna go through all of the empty spaces because you can see that none of them are having the value of number max safe integer. One. So it doesn't have that, which means that we will go through all of the dots. So that will help us in our development, which means that we can basically throw this part of the code out, leave it in, it will only run once. And now we can actually solve the problem. What is the problem? The problem is that we are allowed to cheat once. We are allowed to transport ourselves through a wall once. So, for example, if we transport ourselves, we are going this way and then we transport ourselves through this wall. We get here and we can continue. Or we can transport ourselves through that wall, or through that wall, or through that wall, or through that wall directly to the end. And we will have, let's say that we have 14 cheats that save 2 picoseconds up to one cheat that saves 64 picoseconds. And we need to find which is the best cheat. Well, a simple way to solve this would be basically remove any wall and do a flat fill just like we did. Do a flat fill on the grid once more, and then remove the next one, do a flat fill, remove the next one, do a flat fill, see what the value of end is. This will work, and we actually solved task number 6 in exactly that way. We're gonna go each one by one, we're gonna change one item in the maze and see what the result is. But that's also the slowest solution so far. I ran all the solutions so far, and that one takes around 85% of the total running time, so it's a prime candidate for optimization. So let's try to pre-optimize that, and we're gonna kinda use actually every invariant that we determined so far. So let's get on to that. So let's fire Excel and do a bit of analysis. So imagine that we are in this place. So our thing is here, and we have walls on some sides. So how far can we get along if we basically are allowed to go through one wall? So we can get here or here by going this way or this way, doesn't really matter. We can get here, 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 and here. So we have 4 and 4, 8 different neighbors which are basically 2 away. So what we can do is actually run through all of those neighbors. So we can have, we need to take into account all possible open cells, basically. So from an open cell, how far can we get by teleporting through a wall? So let's just loop through our maze. Yeah, let's get the width and the height. So we're looping through the height, and we're gonna loop through the width as well. We're gonna get the cell. If it's an open cell, we don't really care about that. So if our cell is an open cell, actually we can also have it the other way around. If it's a wall cell, continue, since we don't really care about that. So now we have our cells. So let's find out the neighbors. GH and that is an array, and that's not going to be the standard one because it's going to be, first of all, let's have the ones that are 1 2 over, and then we're going to have the next ones which are, yeah, that one that's over there. So the ones that are in have a difference in both direction, but the difference is 1. So if that is our position, this is -1 on x and y, and so on and so forth. So these are the 8 neighbors, and of course we're going to filter them by width and height. So we have several neighbors, and we're going to filter them also. Yeah, we can map them to the cell, and then we can filter them by being an open cell. Yes, this is exactly what we want, because now we're going to get all our neighbors which are open cells. And let's see what the distance will be. Let's say we will have max cheat is gonna be 0. And we're gonna loop through the neighbors. I don't like using for each. I call this neighbors, which is an awful name. So the distance. The cheat will be the neighbor distance minus the value of the cell. That's how much we will cheat. And this can actually be negative as well sometimes. We don't want those, but basically nobody is stopping us from this cell if we go through the wall, through two cells basically, to get here. Right now we're not insisting that this be a wall. You can basically skip ahead in this direction as well, only you won't get anything by it. Also note that from this point we can actually end up at this point, which is the regular path that we will take. So we will cheat by having no cheating. That's not fun at all. So basically we're gonna look for cheats that save us more than, that save us some time. So the time they will save us will actually be this thing, but if we subtract 2, because we will actually need to move to that place. So if we are moving from value 10 to value 12, we are not cheating at all. If we are moving from value 10 to value 14, we are cheating 2 only, not 4. So that will be the actual cheat. And now we can say if that cheat is bigger than the maximum cheat, that is the maximum cheat. And that is the actual maximum cheat for the cell. And let's console log that. Has that many neighbors? Not that I care, but we want to find the cheat. And so we're gonna need to find the maximum cheat. And it's gonna be just the same, only now we're gonna loop through for the cell. So if the cell cheat is bigger than the maximum cheat, that becomes the maximum cheat. And of course, we're gonna return the maximum cheat. Let's see if this gives us something. Oh, we don't want to do it on a file. We can just see it on the console. The maximum cheat, I think, was something like, we have neighbor, but our cell is, sorry, this is an open cell and this is also an open cell. So what is the problem here? Const cheat. This is something connected with different versions of TypeScript, and it says it's not really sure whether the neighbor is actually an open cell. If we enforce this here, oh, that's a boolean, so it's not gonna do the casting. Yeah, let's yeah, doesn't want to do this here. Yeah, let's write some ugly code. We know it's gonna be an open cell. We got it. So we have a lot of things that have a cheat of 0, and we have one that has a cheat of 64 and a 38. Let's see the description. Yeah, we had a cheat of 38, we should have a cheat of 40, and the maximum is 64. Yeah, that is quite cool. Let's just remove the ones that have a cheat of 0. Cell cheat is bigger than 0, then let's show that. This will be a bit cleaner, because of a lot of places are basically bad places to cheat. We don't gain anything. So we had 36. We only got one 38. Oh, there should be 138, but there should also be a 40 somewhere. Yeah, here. I don't actually see a 40. That's concerning, but on the other hand, we got a 64. Let's try this on the bigger input. And if we have a bug, we will solve that bug in part 2. Now, the result that we need is not actually the biggest cheat, it's the number of cheats that are over 100. So it seems that we have a cheat that will enable us to cheat for over 9,000, which is huge. But on the other hand, it kind of makes sense because the start and the end are quite near each other. So if we are able to, for example, get to from the start go here, we might be able to go directly to the end. So I'm not going to do that analysis, but I will just say now, these are the cheats. That's an array of numbers that's going to be an empty array. So we're going to have our cell cheat and we're just going to push it to the cheats array if it's more than 0. If it's 0, we don't care about that. So out of the cheats, return once. Count. Do we have count? No, we have filter. Cheats that are bigger than 100. Oh, what is the exact wording? Let's save you at least 100 picoseconds, which means that it's gonna be 100 or above, and we will get their length. So this will say that we have total of that many cheats. I half expect this to be wrong, but let's see. No, that answer is too low. We're missing some cheats, so we will need to take care of that in the next part. Anyway, if you liked this analysis so far, we didn't solve the task, but we got close, I would say. Click like, share, subscribe, and